So now it's my pleasure to introduce to you today's speaker, Dr. Ian Campbell. So Ian is an attending physician here at CHOP and DBHi and the Division of Human Genetics, and also faculty at the Perelman School of Medicine at Penn. He completed his MD and PhD training in human genetics at Baylor, and he also completed his combined residency in pediatrics and medical genetics, as well as a fellowship in clinical informatics here at CHOP. I think he's the only person at CHOP who is board certified in all three specialties. So we're really pleased to have Ian speak with us today. I won't go into many more details, but Ian has already accomplished much during his academic career. Numerous publications, national presentations. He just secured a K Award. And I want to personally share too that Ian is an outstanding educator. I worked with him for many years while he's been at CHOP, just an amazing mentor. He's also co-leading efforts to expand data science and informatics education to non-informatics trainees and faculty at all levels. So something that we're really excited about as well. As you will hear during today's presentation, Ian has very nicely developed a unique area of expertise at the intersection of clinical informatics and genetics genomics. His primary interest is in extracting phenotypes relevant to genetic disease from the electronic health record, and then using them to improve the diagnosis and care of children. He also focuses on how genomic data can both be entered into a patient's EHR and then how that information can be used by clinicians to improve their care or the care of patients. And I would add also to improve access and more equitable care. So today, Ian will be speaking on harnessing the EHR for timely diagnosis and personalized management for children with rare genetic diseases. And before I pass the microphone to Ian, I put in the chat, we definitely plan on having time for questions at the end of Ian's presentation. We ask that you enter your questions into the chat function. Please mute your microphones, turn off your cameras, as I mentioned. And there's even live captioning features in Teams, so you can take a look at that in the chat as well. So again, we're really very excited to hear from Ian about his very innovative work. And with that, I will hand it over to Ian.
Thank you so much for that wonderful introduction, Tony. I really appreciate it. And since he already gave you the title of my talk, I will just jump right in. And so the mission of my research is for every child with a genetic disorder to receive as accurate and timely a diagnosis as possible. And that's a really lofty goal. But I try to use the electronic health record in multiple ways to work towards that. And here's a picture of a patient that I cared for or was involved in the care of as a graduate student way back at Baylor. And I try to do the same things now that I did back then, which is improve care for kids with genetic disease. And just so that we're all on the same page, the purpose of a clinical genetics evaluation is to identify one or more genetic changes that causes a unifying diagnosis for a patient. To explain their medical problems. And such a diagnosis might allow for prognostication about future motor and neurocognitive development. It might identify additional organ systems that potentially require surveillance. It might inform the recurrence risk for other family members or the patient themselves. And in some cases, there may be specific interventions or rarely molecular therapies that are available for a particular thing. And so if everybody could just remember to mute their microphones, that would be great. And so unfortunately, the healthcare system as a whole doesn't do a super great job at caring for patients with rare genetic diseases. And a little over a year ago, the UN General Assembly passed a resolution urging member states to strengthen their healthcare systems to address the issues that patients with rare disease have. And even former President Obama recently mentioned that precision medicine genetic care has not progressed as fast as he would have hoped. And so, we need to do more to help care for patients with rare genetic diseases. And from my perspective, I think there are two major barriers to precision genetic care. First, the patient has to have been accurately diagnosed with a genetic condition. And second, the patient's healthcare team must be familiar with any recommendations for that condition. And so I'd like to focus on the second one for a little while, and then we'll come back to the first. And so let's be realistic. It's nearly impossible for clinicians to know all of the management recommendations for a genetic disease, particularly if they haven't remembered hearing about it since medical school, or if it's the middle of the night in a busy ER. And this is exacerbated by the fact that there are more than 5,000 known genetic conditions. And so it really is literally impossible to know everything about them. And so the solution to this is just-in-time clinical decision support, where the important recommendations are presented to a healthcare provider right in the moment that they're needed. But there are two ingredients that we need to be able to do this. First, we need to have computable genetic variants in the EHR ready to trigger the clinical decision support. And then second, we need to have machine interpretable instructions for these highest yield recommendations so that they can be presented to the providers. And so at CHOP, in the previous state, genetic results came back in a PDF report, or sometimes directly, transferred into the EHR. And so then the genetic changes, like this variant of RYR1, was stuck either in a PDF, which can't be computed on, or in a semi-structured text, and really hampered using this data. And I think we can agree that a more ideal state would be if, instead of being in a table in a text document, it was in a database in the EHR where it could be computed on. And so previously, when the genetics lab here at CHOP, the division of genomic diagnostics, completed a genetic test, they'd manually create a report and send that into the EHR. But thanks to a concerted effort by the hospital, now we send a computerized message from the CHOP genetics lab that actually provides that DNA variant information directly into the EHR. And once that variant information is in the EHR, we have a fancy thing called a translation engine, which converts those DNA variants into genomic indicators, which are Epic's way of keeping up with genetic conditions and risk factors. And then based on these genomic indicators, we can provide education to the patient's care team. We can provide education to the patient and their family through MyChart. We can deliver personalized clinical decision support based on the genetic condition. And then also, importantly, we can deposit those DNA variants and genomic indicators into the CHOP data warehouse so that other people can use this information for business analytics, quality improvement, and research. And so it only took me a minute or so to talk about this new clinical workflow, but it really was a huge multidisciplinary effort, which required vast amounts of resources and dozens of professionals from across the hospital, including some of which that I have been able to show the pictures and names of here, including Marianne Hennon and John Potter from Information Services. And many more that there's not room to show pictures of. But it really was an amazing giant project, which we really came together, and I was just a tiny part of. And so we started with 28 cancer predisposition syndromes. Each one of these, if a patient has a pathogenic variant or in these conditions, that they have an increased risk of particular types of cancers. And each one of these cancer predisposition syndromes is on a list of important secondary findings made by the American College of Medical Genetics. And these are so important that the college feels that if we know about them, we have an ethical obligation to tell patients about them because it could influence their care in meaningful ways. And so here's what one of those genomic indicators might look like to the patient. If they have TP53 variant causing Li-Fraumeni syndrome, there's a section of MyChop which has some education about that condition and what sort of things that might mean, like cancer surveillance or reduced radiation exposure. And so here's what that genomic indicator looks like to a provider in a particular place in hyperspace, the EHR that we use to take care of patients. And then we wanted to think about the highest impact clinical decision support for these conditions. And so according to the Institute of Healthcare Improvement, there are 5 rights to good clinical decision support. It must be the right information to the right person in the right format, in the right channel, at the right time in the workflow. And so we felt that the right time in the workflow was just when the provider was caring for the patient. And so we started with a referral to cancer predisposition clinic, clinical decision support alert, so that if a patient has not had the opportunity to establish care with our world-class cancer predisposition program, it would gently advise caregiver clinicians, say in a primary care office or specialty care, that this patient hasn't yet seen cancer predisposition. Would you like to refer them? And then for patients with Li-Fraumeni syndrome and RB1, these patients are highly sensitive to ionizing radiation. And so we created a clinical decision support alert when providers try to order a radiation including procedure, that these patients are at increased risk from ionizing radiation. Would you consider, talking to radiology or to genetics to think about an alternative? Noting, of course, that in an emergency, these patients can still, receive an X-ray. And so that was a great, great additions to the EHR. And going forward, as new patients have new genetic variants identified, it automatically applies these indicators so that they can benefit from our interventions. But we've also taken care of hundreds of patients historically that have these conditions, and we also wanted to make sure that they were able to benefit from all this work. And so we wanted to identify historic patients. First, we tried using some simple natural language processing, which had really great accuracy, but not so great recall. And so, we felt so strongly about this that Matt Dulick, one of the lab directors in the DGD, and I, manually reviewed hundreds of patients' charts to try to find patients that have pathogenic variants and a diagnosis of one of these conditions. And we found 204 historic patients that can benefit from this as well. And we're very close to pushing the button to add these patients any day now. And so, that was a great first step. But we want to look towards the future. And so with executive sponsorship from Bimal Desai, the CMIO, and Cherie Perdue, we formed a standing genomics and precision medicine committee, which includes members from different disciplines to shepherd our genomics vision going forward, selection of new indicators and review existing indicators as medical knowledge advances and things change. And we also developed a standard procedure for developing new indicators going forward. And so I don't expect you to read every item in this flow chart, but just know that we identify subject matter experts and then figure out how we're going to improve the healthcare of a new group of patients. And so we've been working with Alyssa Ritter in cardiovascular genetics and some great cardiologists. In fact, we met this morning working on the next set of conditions and how we'll improve their care. And we've also developed an intake form for new projects. And so if there is a genetic condition that you're really passionate about, we'd love for you to fill out this form and tell us how you want to change the patient's care and send that to us so that we can think about how to get that on the roadmap for the future. And so just email me to let me know if you'd like a copy of this. And so in summary, we've implemented a genomic pipeline that goes through our AHR and that begins in the genomics lab and ends in personalized clinical decision support for patients with particular rare genetic diseases, cancer predisposition syndromes. And to oversee this really complicated workflow, we've chartered a genomics and precision medicine governance committee, which meets regularly to shepherd this process forward. And so hopefully I've been able to show you how at CHOP we are trying to change the EHR to better deliver precision genetics care. But as I mentioned before, in order for that to happen, a patient has to be accurately diagnosed. And to be diagnosed with a genetic condition, somebody has to think to send genetic testing. And so I'd like to talk to you about how my research group is working on that. And so in order to have the right framework of how to think about this, it's helpful to think about how genetic diseases were diagnosed before the widespread availability of exome sequencing and other whole genome sequencing genetic testing methodologies. And before all that was available, there were things called clinical criteria to help diagnose genetic diseases. And so, these are elements that when they appear in combination define the presence or absence of disease. And these elements include medical problems, physical examination findings, laboratory test results, imaging findings that when you have some of these, then you meet criteria. And so here are the Curarino criteria for hereditary hemorrhagic telangiectasias, a particular genetic disease. And so if you have 3 or more of the things that are listed in this box, then you meet the diagnostic criteria for HHT. The problem with this is that criteria are almost exclusively developed by expert consensus in genetics. And there's really no estimate of sensitivity or specificity for these criteria in most cases. I actually showed HHT's criteria because it's one of the rare exceptions where a couple of years ago, some researchers tried to assess what the sensitivity and specificity of those criteria are. But you could imagine that if the criteria have poor performance, that might lead to missed opportunities for diagnosis, or it might lead to unnecessary testing or interventions. And so another example of a disease with clinical diagnostic criteria is nevoid basal cell carcinoma syndrome. And this is also called Gorlin syndrome. It's a cancer predisposition syndrome characterized by basal cell carcinomas of the skin. And in adulthood, patients often have hundreds of basal cell carcinomas. They are at risk for other types of cancers like medulloblastoma. And then there are many other associated medical findings such as jaw cysts, which you can see here with the orange arrow on this x-ray, and then palmar pits. If you soak the patient's hand in warm water, they develop these pits on their skin, and these things can help with diagnosis. And Gorlin syndrome is a particularly good example because there's the exciting potential for molecular therapy with hedgehog pathway inhibitors to prevent the basal cell carcinomas. And so there are existing criteria which work pretty well for adults, but we felt like the criteria have poor sensitivity for children. And we wanted to improve the criteria, but we didn't really have a framework. And so my collaborator, Nina Gold, who was a genetics fellow here at CHOP and now is at Harvard, she surveyed 48 participants with Gorlin syndrome and asked them what sorts of medical problems they had. And so here on the x-axis is the age of the participants in years, and then on the y-axis is the various features that they reported and the age that they reported them. And so you can see that patients have macrocephaly, often present at birth, but they don't develop their cataracts until much later in life. And so we standardized the results of our survey into HPO terms, a standardized terminology, which we'll discuss a little bit more later, and then the age at which those patients reported the symptoms, and then we determined how many of them fulfilled the criteria. And so you can see on the x-axis is the age of the year in years of the participants, and then what percentage of them fulfilled the existing diagnostic criteria. And so you can see that it works relatively well in adulthood, but particularly during early childhood, not so helpful. And so we used information from statistical methodologies and our clinical expertise to iteratively propose new criteria until we had arrived at a set of relatively simple criteria that we felt outperformed the existing criteria in childhood. And so you can see that our criteria, result in, say, 50% sensitivity, at age 7 compared to the existing criteria in the teens percentage of criteria of sensitivity. But what about the specificity? As people on the call will probably know, you can make an 100% sensitive set of criteria if you make them very poorly specific. And so we didn't really have a good way of doing that. And so we landed on a simulation approach. And so we simulated control patients with air quotes by randomly sampling phenotypes that are associated with genetic diseases from a major database. So here's OMIM disease number 151623, and we sampled some phenotypes that are associated with that condition to make simulated patient 1. And then we take a different disease and sample some different phenotypes for patient 2. And then we do this many, many times until we have a whole cohort of simulated patients. And then we simply ask how many of those simulated patients would fulfill the criteria if we applied them to them. And so there's no information about the age of onset in OMIM. And so we only have the estimated specificity at adulthood. And so what we found is that the current criteria, the ones that work really well for adults but not so good for children, are exquisitely specific. Basically, nobody else fulfills the criteria except for patients with Gorlin syndrome. While our criteria have about 85% specificity, but critically, this is among patients with genetic diseases, not the general population. And so we felt that this specificity still had clinical utility. And so we were able to publish our criteria and our framework last year. And so I do want to, say though that there are some limitations to our approach. First, we used simulated patients instead of actual ones, which obviously would be better to have real patients. As I mentioned, there's no information about the age of onset of the symptoms, so we can't do, age-based specificity. And there's no information about the phenotype prevalence within the diseases for most diseases. And so, even though macrocephaly is very common in Gorlin syndrome and cataracts are relatively uncommon, we don't have any information about that to do our sampling. And so a key goal of my research is to amass a large cohort of children with suspected genetic diseases with structured and chronological deep phenotype information so that we can do things like estimate specificity for diagnostic criteria and do all sorts of other exciting research. And so, I take EHR data of various types and try to distill that down into discrete phenotypes. And so I'd like to do a deep dive in how we're trying to do that, particularly for physical exam information. But before I get to that, I just want to touch on the human phenotype ontology, which is the terminology set that we use to structure our genetic phenotypes. And there are about 17,000 terms in the HPO, and they're organized into a directed acyclic graph. And if you're not familiar with what that means that it's directed because there's a directional relationship between terms in the HPO in that fifth finger clinodactyly is a type of clinodactyly. And it's acyclic in the sense that it can't go around in circles. There's only one direction down to more precise terms. But there can be multiple parent-child relationships between terms. And so finger clinodactyly, as I mentioned, is a type of clinodactyly, but it's also a type of deviation of the finger. And then there is a specific term for each of the fingers, fifth finger clinodactyly. And so you can see how it's organized. And this is useful because it was specifically developed for human genetics and has been in wide use for decades. And it's widely used in clinical diagnostic testing pipelines, including here at CHOP in our division of genomic diagnosis to inform exome sequencing. And importantly, it's computationally tractable, and we can use a lot of tricks from graph theory to be able to use HPO terms to understand the similarities between diseases and patients and things like that. And so one of the things that you can categorize using the HPO is the dysmorphology physical exam, which I hold as a very rich source of phenotypic information for genetics. And these are physical differences that clinicians like me, note when we see patients, like up-slanting or down-slanting palpebral fissures, or rotation of the ears, posteriorly rotation of the ears. And we note these down in our physical exams. And we also take specialty anthropometric measurements, like how far apart the eyes are, and then use specialized growth charts that we carry around with us to assess, is this typical for a given age group? And so, I have here sort of the classic way of documenting a dysmorphology physical exam in EPIC for the non-clinicians that are on the call. You can see that people might select from a drop-down list some of the phenotypes that they found. But then, if there's not a lot to say, they might select the default button, which pre-populates the note with the defaults, the default normal things. And it's important to think that, maybe I didn't think so carefully about what I did there when I pushed the default button. But I, enter in the measurements that I've taken and the percentiles that I've calculated for my growth chart. And then I might go back and add some things that there weren't any drop downs for. And so I think it's important to note that, this document that I just prepared doesn't really have a lot of information in it as far as positive, phenotypes that the patient has. There's dolichocephaly and hypoplastic alynase that I've written there, but all the other stuff is just default stuff that I added from the template by pushing that all defaults button. And so my preceptors at CareBots, when I was a first-year intern, warned me to use that button very carefully because it's easy to gloss over things. And so we hold that by removing those default normal findings, we can enrich for meaningful information that's been documented in the patient's physical exam. And by analyzing years and years of physical exams from genetics, we can find that almost 80% of all of the text in these key craniofacial organ systems is actually default text. And there's, in about half of observations, there's only default text and no other information. And so I thought that it would be a good idea to try to segregate this default information from the really important phenotypes. And so I created a new system for the entry of the dysmorphology exam using an Epic Smart Form. And so there's buttons for common findings and then a free text field for you to write the things that are notable about the patient. And then in order to save time, we've got boxes for the measurements that we take, and it automatically calculates percentiles, so you don't have to use that growth chart anymore. But still, there's a macro for you to push so that you can get that normal stuff, but it's separate from the important positive findings. And so after you push these buttons, it automatically generates the text for your note. And another important feature of this is that when you click on an abnormal finding, it prevents you from making logical incompatibilities where normal head size and shape doesn't go together with frontal bossing. And so while it speeds the clinical workflow, as I mentioned, you can imagine that one of the impetuses for me to make this was so that I could collect those phenotypes later. And so when you click on the low set button in next to ears, later I can get the HPO term for low set ears out of the database. And so here's a graph that shows the number of abnormal phenotypes that we've documented per individual for over 2,000 patients that have been phenotyped using the system over the last couple of years. And so you can see that a little bit more than a majority of patients have at least one HPO term that's abnormal that's captured by this system. And you can see that some patients actually have multiple abnormalities that are captured. And so here is, the distribution of those things with the number of participants on the x-axis and the various number that have these HPO terms on the y-axis organized by system and frequency. So you can see there's a good distribution of things, that we've been able to capture. But what about that free text information? Say somebody writes mildly overfolded right superior helix, left mildly squared off. How do we get useful information out of that free text? And so to clarify, just so that we're all on the same page, the goal here is to take this text and recognize the words overfolded superior helix go along with the HPO term for overfolding of the superior helices, and then superior helix, the other one is squared off, goes together with this squared off superior portion of the helix. And so it turns out that this free text to HPO task is actually a hot item in biomedical research. And there are some tools that are developed to be able to do this. And two of them that I wanted to focus on, one, Phenotagger, which is sort of the one to beat, which is made by a lab at the NIH, and Doc2HPO, which was partially developed here at CHOP a number of years ago. But most of the tools have some drawbacks. For example, Phenotagger is really good at finding a precise concept like fifth finger clinodactyly, whereas it has no idea about negation. And so if a clinician writes, no scoliosis, Phenotagger will happily tag scoliosis. Whereas Doc2HPO has negation detection and so won't tell you about scoliosis the patient has. It doesn't really have as good of concept precision, and so it might identify clinodactyly in place of the patient's fifth finger clinodactyly. And so we felt that we could do better than the existing systems for HPO extraction, and so we set about the process of developing a new model. And so to do that, we need data, because machine learning, really, the magic of machine learning is training data. And the first source of training data that we use is from the HPO itself. And so if we look at the HPO code for type D brachydactyly, which is a phenotype that I actually have myself, there's a synonym in HPO which says, a synonym of type D brachydactyly is brachydactyly type D. Very helpful. And so then we can actually go to the NIH's UMLS Metathesaurus and look for a mapping between HPO terms and Metathesaurus concepts. And so in the Metathesaurus, we find that there's brachydactyly, type D as a synonym for type D brachydactyly. And then once we're in the Metathesaurus, then we can go on to other terminology sets like SNOMED-CT and MEDRA and OMEM, and we might find even more synonyms for type D brachydactyly. And so, for example, if we go to OMEM, we can find that somebody thought that stub thumb was, a synonym for type D brachydactyly. And so we can collect all this data and use it as true positive training data. But we're trying to solve a clinical problem. And so we also wanted to, have clinical training data. And so we generated manually annotated data using a novel interface that I developed in R-Shiny. And then 3 medical genetics trainees that are listed below and a medical student, Mary, and I annotated thousands of clinical texts. And so if you'll recall the task of mildly overfolded right superior helix, left mildly squared off, we want to find those HPO terms. And so we've started off at the top with what Phenotagger thinks is the right answer, and unfortunately it hasn't gotten either of them totally correct. But overfolded helix is pretty close, so then we can click on details and look for a subclass overfolding of the superior helix and go ahead and add that one. It really missed the squared off helix, and so we can search for that using our search box. And once we've found the 2 correct HPO terms, now we just need to tell the system where in the text those terms are located so that the system can learn from that. So we just highlight those areas and add the spans, and then start working on the second one. And this is the process for one physical exam organ system free text observation, and then we do this thousands of times. And so we also annotate those explicitly mentioned negative findings in case we want to use those to further train our model later, but I didn't have an opportunity to show you how that worked. But thus far, we've annotated 3,673 organ system observations, which is by far the largest annotation of HPO terms and physical exam findings available anywhere in the literature. We did some inter-annotator agreement of 890 observations that were, annotated at least twice, and there was 76% complete concordance between the annotators, where each annotator had the exact same set of exactly the same HPO terms, and which is actually very good for such a complicated task. And it's very likely that there were probably mild disagreements for maybe a more specific or less specific term very close in the HPO hierarchy, but we haven't evaluated that much more. And so having collected all of that training data, now we can use it to create a new machine learning algorithm to identify HPO terms. And so I've been really lucky to be able to work with Xinwei Zhao, who is a data scientist that works with me to work on this model. And so we use PyTorch as our machine learning framework. And then we have developed a model where we take our sentence, say moderate hypotonia of the trunk. We use a tokenizer to break that into individual pieces. And then we use a large language model, in this case, bioclinical BERT, to create word embeddings, and then have a recurrent neural network layer to extract the text representations, and then a fully connected classification layer, which outputs probabilities of HPO classes. Hopefully at the end, it has the highest probability for axial hypotonia, the correct answer in this case. And so here are some preliminary data of single angle classification performance for our model compared to the 2 other big name classifiers in the field. And so you can see that we have considerably better performance, paying attention to F1 score, which is commonly used in machine learning performance, which sort of takes into account both precision and recall. We are doing pretty well compared to Phenotagger. And here are some illustrative examples. Obviously, I'm going to try to impress you with the examples, but still, if the observation is mouth, high intact palate, Phenotagger just got wide mouth. Sometimes it's sort of really puzzling how these things arrive at their answers. And doc to HPO didn't have anything, whereas our model got it correct. And then clinodactyly of the fifth finger. Doc to HPO got clinodactyly, but not of the fifth finger, whereas our model can. And then in a more complicated case, we've got axial freckling : no, inguinal freckling : no. Both Doc to HPO and Phenotagger have gotten confused by the linguistics there, whereas our model, because of the power of BERT, is able to understand how that colon works. And then as far as, another example, the prominent forehead, only with a misspelling, neither Doc to HPO nor Phenotagger is able to identify that, but our model can see that as, a common misspelling. And so in summary, we implemented a dysmorphology exam system that speeds the clinical workflow and captures structured data. We created a user interface to annotate physical exam observations with HPO codes, and then developed a novel text classifier to get those HPO codes out of the free text. And before I go on too far, I just want to say that the magic of these state-of-the-art NLP algorithms is the large language models. And so we used bioclinical BERT, but these types of large language models are really in the news. For example, GPT-3 has really made a big splash with the chat interface to that, and big tech companies are throwing huge sums of money at the development of these. And so just as an example of how we can use those and what the future might look like, early in the development process, we started with BERT, which was made by Google and was trained on thousands of books and Wikipedia, many billions of words. And then in our early model, we got an F1 score of 59.95. And then we heard about BioBERT, which was made by a lab in Korea, which also includes PubMed abstracts and PubMed Central and other 18 billion words. And just by switching out that language model, not changing any of the parameters or anything, we actually got a couple of percentage of improved F1 performance just by switching out the large language model. And then, then came bioclinical BERT, which had all the things from before, only also clinical notes from the MIMIC data set. These are adult critical care, heavy progress notes and H&Ps, another 700 million words. And we got another couple of percentage points. And so I think that CHOP should, use its EHR data as training data for, say, a PEDS BERT, where we can include the over 10 billion words in our EHR progress notes, to make a new general purpose large language model to help improve the care of children. And who knows how much better performance we can get from that. And obviously, we can create a PEDS BERT by pre-training on our data, and we can use PEDS BERT inside the CHOP Research IS infrastructure environment or in ARCIS to do new general purpose tasks. But I think we also may have a little bit of a responsibility to release something like that to the public so that it can improve the care of children all over the world. But obviously, there are some privacy concerns about large language models, which if people are interested in, might be able to talk about in the Q&A session. But I talked about the physical exam and thinking about the other sources of deep phenotype information like medical problems and imaging findings, things like that. The goal is to distill all that down into computable and chronological phenotypes. And so here's a table of just different data sources and how we can collect hundreds of thousands of HPO terms about tens of thousands of patients that have been cared for by genetics over the last decade and a half. I do just want to say, though, that phenotype extraction is not quite as simple as running your fancy state-of-the-art natural language processing algorithm on every node. Because if I apply our model to this genetics consult note that I wrote about a fictitious patient, we might extract these HPO terms and feel really good. We got deep phenotype information about this patient. But if we look lower in the note where I'm writing my assessment, maybe talking about the differential diagnosis and what things might be associated with that differential diagnosis, if we run our model on that, then all of a sudden we're extracting phenotypes that are in the differential, not that the patient actually has. And so, you can see that I was talking about vectoral association, and we can detect, for example, tracheoesophageal fistula. that is something that the patient doesn't actually have. And if you're trying to make a tracheoesophageal fistula cohort, that could be a big problem. And so to overcome this, we're working on improved methods to identify specific note sections. So, the HPI and only extract from the HPI in review systems and physical exam, for example. And there has been some work in this regard in adult populations, but as far as I'm aware, there's really nothing in pediatrics. So, an area for improvement. And so, if we assemble all this deep phenotype information about our patients, that's great. It's a great resource for investigators all over the hospital, but what are you going to do with that? And so in the future, I want to use those deep phenotype information, to develop human usable and computational evidence-based criteria for genetic disease. And so what we could do is we can identify how long since health system contact patients with particular genetic diseases were diagnosed, when their genetic disease was noted. So here's a little over 2,000 patients. And then if we apply our methodologies, how much sooner could we possibly diagnose those patients? And so here's a simulated improvement of 25%. And so we might also use that same phenotype information to develop user interfaces for other clinicians to develop their own criteria. So you could imagine that somebody might be designing their criteria in a web interface, and then they might get real-time feedback on specificity and sensitivity as they're designing it, so that they can get an idea about whether or not their criteria will be performant. And then finally, we can apply these computational diagnostic prediction systems at the health system level to try to identify patients that may be at risk for genetic disease. And so many studies have shown that there are major inequities in genetic care and how it's delivered. And individuals from historically marginalized backgrounds are referred to genetic specialty care at lower rates. They're provided access to indicated genetic testing at lower rates, and they're more likely to experience genetic mixed diagnosis. And so the reason for that inequity is certainly multifactorial and something that I can't possibly hope to solve, but I can try to do a small part, potentially by providing clinical decision support to patients that are at risk, so that their providers are cued to think about whether referral to genetics might be appropriate. And so in conclusion, I hope that I've shown you how we're intervening in EPIC to care for patients with rare genetic diseases. We're improving EPIC in ways to better capture phenotype information, and we're leveraging natural language processing to further enrich our phenotype data. In the future, I really hope that we'll be able to predict patients who might have undiagnosed diseases and notify their clinicians to prompt genetic diagnoses. And so I would really like to thank all the people that have made this possible. And I just want to say that, CHOP leadership has really had the vision of making data accessible. And so if, all the people that were thinking about data access long before I came to CHOP hadn't been ready to make data accessible and usable through things like the CHOP data warehouse, I'd never be able to do any of the things that I've showed you today. And then obviously I want to thank all the people that have helped with the genomic indicators and the dysmorphology physical exam, including Morgan McManus, the genetic counselor who helps me take care of patients in the clinic, as well as my collaborator, Graciela Gonzalez-Hernandez, who helps with my natural language processing, and then Dr. Halkinarson and Dr. Zakai, who have been just amazing mentors to me. And so I am really excited to be able to take some of your questions.
Great. Well, thanks very much, Ian. That was really a very impressive talk, and we've already started to get some questions in the chat, but if other members of the audience, we have up to about 135 people, would like to ask some questions for Ian, please feel free to put them in the chat and we'll get through some of them. Ian, I'm not sure if you can see the chat, but there are a couple of questions asking about, first of all, a number of real excellent comments about your presentation and just the generalizability, I think, of all the work that you're doing. Really great talk. Some questions. Are you annotating all genetics notes with HPO codes using NLP? If so, where are they stored? And I think kind of a corollary, are you extracting from all nodes or limiting just to the genetics service at this time? So maybe we'll start there.
Yeah, I think that's really the question. Obviously, we could apply these techniques, at scale to every note, but then it wouldn't necessarily give us the information that we're looking for because of all the differential and the associated things. It's not just genetics that likes to wax on poetic about the differential and the things that are associated with that. If you look in other subspecialty notes, you'll see the same sorts of issues about that. And so it's going to be really important to develop segmentation algorithms to get the highest quality phenotypes out of the different sections. And so for just genetics personally, we only have a set number of templates that we've used over the decades. And so I can just write regular expressions to get the different sections out. But we're going to need a much fancier algorithm to have it more generalizable, hopefully at some point to extract information from all of the wonderful pediatric subspecialties that we have here at CHOP. And so not quite ready to make this go to the entire health system and provide HPO codes for all. But that is on the roadmap and something that I definitely want to share with everyone else. And I will just jump into, I hope that answered the questions. I didn't want to skip Kevin Johnson, Dr. Johnson's questions.
Yes, please, yeah.
Yes, this is the EPIC Genomics module. We have regular meetings with our friends from Verona, and the genomic indicators are the genomics module. And I think hopefully I answered. So Dr. Sullivan is asking, how big of a hurdle do I think rolling something out like this to the whole healthcare system would be? So one good thing about EPIC having somewhat of a duopoly monopoly type situation is that the Clarity data model is certainly different at different institutions, but it's not that different. And so it's not that hard to apply to notes at another healthcare system, but I'm not ready to do the entire CHOP health system, one little thing at a time. I don't think it's impossible, and I think it would be certainly useful. And I definitely am interested in collaborators at other children's hospitals to help us not to train a system that's really good at extracting phenotype information from CHOP patients, when it would also be great if it could do it from Children's Hospital of Cincinnati or wherever else, CHOA, for example. And so then Kai Wong said, let's talk about the privacy issues. And I promise I did not plant him in the audience, but I would love to talk about the privacy issues. And so let's talk about what a large language model is. And so, Google, they took their Wikipedia articles and their books, they extracted some text. Here's a random sentence I got from a random Wikipedia article, and then they take a sentence and they mask randomly one of the words, like this one. And then it trains the model over trillions of iterations to guess what that word is supposed to be. And so, Bert may be able to see that mask and say, oh, state goes after US blank of Oklahoma. And over time, it gets better and understands human language. And so then our friends at MIT, they might have gotten this sentence out of, the EHR at Brigham and Women's, and we're like, the E. coli was resistant ampicillin, but susceptible to ceftriaxone. Mask out the susceptible, and maybe it learns that susceptible is the word that goes in there, and so it learns better about how clinical text is structured. And so my vision is that, more pediatric focus. Say we write, due to hyperbilirubinemia, she was treated with phototherapy. If we blank out phototherapy, if we ask actual bioclinical BERT what the answer to that is, it's going to say fluids, because it doesn't know, a lot about pediatrics. And so we want to train something that's able to know things about children's healthcare. And so you can like download Bioclinical BERT right off the Hugging Face website. It was downloaded like over 1 million times last month. And so I think, you know, we can be leaders in the understanding of children's health information. But what exactly is, you know, a large language model? It's really just a set of tokens, which are, you know, not really words, but, you know, parts of words often. And then just a big collection of decimal numbers that relate all these things together. And so if you release a large language model, you're not releasing private health information per se, but the problem is that you could imagine that, say, you know, we've got a sentence here that, you know, is in a health record somewhere. You know, Maylee Bowlesby Duckworth is a 4-year-old with autism. You know, that's Senator Duckworth's child's name, and I don't think she has autism. But you could imagine that if that was written down somewhere, if I trained a model that you know, learns what goes in the blank there, that if somebody got a hold of my PEDS-BERT and then did a tax on it to guess, you know, what she has, then they might be able to get back information, you know, better than random chance. And so, you know, maybe PEDS-BERT would say asthma because there are more kids with asthma than autism, but, you know, who knows? And so this is a theoretical privacy risk, definitely, and people have written papers about this. And for smaller language models like BERT, you know, these are, the general consensus seems to be that, you know, it's not that big of a deal. But for larger language models like you know, GPT-2, for example, which had an order of magnitude more parameters than BERT, you know, researchers were able to start an address and then recover the rest of the address from the model because it learns sequences of words. And so one way that we can get around that problem is by de-identification and obfuscation. And so there's this really cool de-identification model made by Stanford, which uses deep learning to identify, you know, oh, this is a patient's name, and this is a numeric ID, and this is a date, and this is a healthcare provider. And then we can, you know, put back in those spots random information that fits along with it to not confuse the model too much. But then an attacker would be, you know, totally unable to recover meaningful information. And then there's one more piece of the puzzle, which is the tokenizer, where, you know, you would think that words are in the tokenizer, but there's this technology called word piece so that the system can recognize words it's never seen before and breaks it down into individual pieces. And so it's not possible to just go and look for all the tokens that are people's words like Flores and then try to remove them, because you can't predict ahead of time what the word piece is going to do. And so I'm really excited to be thinking about these sorts of issues and you know, working with the IRB on how we can prevent you know, privacy issues while still moving the field forward.
Thanks, Ian. That's really, really important considerations. We definitely want to preserve privacy as much as possible. And you know, there are a couple more questions I think you may see in the chat from Asif about PEDS-BERT and also capturing pedigree information in this model. Is that a possibility? And then Kai Wang has a couple other comments. And others, please put any questions in the chat. We have about 2 more minutes before we're at the top of the hour.
Yeah, that's a great question about you know, the pedigree information, and that's something that I think would be extremely useful information, but is not something that I have focused much attention to. I have talked to some great researchers at Geisinger, where it's a, you know, a health system where there are fewer people that move in and out of the community, and so there may be, you know, people that are you know, cared for multiple generations in their health system, and they've done some really cool work with addresses and names and trying to put together a giant pedigree of everybody that they take care of. And so that would be a fascinating thing to apply here at CHOP, but you know, it's not something that I've worked on specifically. And so, Rich, I want to say that I haven't started working on the model quite yet, because I want to make sure that we address these issues. I don't want to spend a giant computation bill to make a really great model and then have privacy issues. But my general plan will be multiple step to, one, first remove manually all of the patient's name and their name history from Epic. So obviously we can get rid of their actual name, the exact matches, and then we can run these de-identification algorithms that identify problematic text and then replace it with obfuscation to decrease those risks. I hope that answered your question.
Well, thank you, Ian. Again, I know we're at the top of the hour, and really what an amazing presentation. Thank you for kicking off our Informatics Talks series. We invite everyone, as I mentioned earlier, to join us each month as we kind of showcase informatics-related collaborations throughout the CHOP enterprise, especially with our DBHi faculty. Thank you again, and if there are other questions, feel free to put them in the chat. We'll kind of get back to you if at all possible. So really, really excellent job, Ian. Appreciate it. But one last note, I want to thank Ari Downs and Donna Vito for really pulling together this series, and everyone. We had just a great turnout. So thank you all.
Thanks so much for listening.